Hi, everyone. On behalf of the Southeast New England Program Network and the New England Environmental Finance Center, welcome to our webinar on emerging drinking water contaminants, brought to you by Weston and Sampson. My name is Leah Soloway from the New England Environmental Finance Center, and I'll be assisting with logistics for today's program along with my colleague Tess Clark from Syracuse University Environmental Finance Center. Before we begin the webinar, there are a few logistics to keep in mind. First, everyone will be on mute to ensure audio quality. You'll be able to ask questions by typing them into the questions box on your GoToWebinar control panel. We look forward to answering questions, so please type them in at any time. Additionally, you can request a certificate of attendance for joining this webinar. Information on how to do so will be available in our follow-up email after the webinar. We have closed captions available for today's webinar. To view the closed captions, please click the link that's available in the chat. Also in the control panel under handouts, we have the presentation available for you to download. And for a little bit about the SNEP Network. Here you can see a map of the Southeast New England program region. SNEP Network's mission is to empower communities to achieve healthy watersheds, sustainable financing, and long-term climate resilience through management of stormwater and restoration projects. We focus on building local capacity by providing no-cost trainings, webinars, technical assistance, communities in the SNEP region. If you want to learn more, please visit our website, snepnetwork.org, for more information. And on that note, I'd like to hand things over to Tess Clark to introduce our presenter for today.
Thanks so much, Leah. It's my pleasure to introduce Steve LaRosa, Senior Project Manager at Weston and Sampson. Steve is a team leader at Weston and Sampson focused on investigation, remediation, and redevelopment of sites contaminated with hazardous materials. Since 2015, Steve has been one of the primary Weston and Sampson scientists in their emerging contaminants group. Steve has investigated many PFAS-related sites and sources and levels of impact throughout New England with all kinds of tools. On top of this, Steve is an excellent science communicator and has presented to various audiences, including the New England Environmental Business Council, and worked extensively across sectors in the Northeast. Before you take it away, Steve, we wanted to quickly ask our attendees today about how you're feeling about PFAS and PFOAs. So please do us a favor and answer the poll question you are about to see. And while folks are doing that, I'll set you up as the presenter, Steve.
Great.
Okay, it looks like we have about most people responding, so I'm going to share the results. And almost half and half, people are very concerned and somewhat concerned. So nobody's not concerned really, just 5%. So it'll be interesting to hear how we move forward from our discussion today. All right, and then Steve, you should be getting a presenter box soon. Were you able to see that share screen?
I am not seeing it this time around.
Oh,
Hang
boy.
on just 1 second. Let me see if it's hidden. I do not see it.
Okay, let me try it one more time. Okay, how about now?
There we go. That's got it.
Sure. Thank you.
All right. There we go. I think we're in good shape here. Can you see that okay?
Absolutely. Looks great.
All right, great. Well, welcome everybody. It looks like from our poll that most everybody does have some concerns with regard to PFAS and their community, which is good to know, and I think is a good condition to be in. Today, what I'd like to do is really talk to you about some of the general aspects of PFAS with what they are, where they come from, why we should be concerned. And then I'm going to go over a couple of case studies. One is for a small drinking water system that was in Rhode Island, and another is actually for wastewater treatment and collection of wastewaters and what PFAS are in those. And then I'll end with a little bit about what there are for resources out there for communities, primarily in Massachusetts. I know that Rhode Island is a lot of folks that are on the call also, and there are some resources there to try and take a look at these particular compounds. But you'll see we're in a state of flux. And then what I'm hoping for is we'll have a nice 15 minutes or so for a question and answer, and really kind of talk more generally about what folks may have for concerns. So again, we're going to see what are these PFAS, why do we care, what's the regulatory status right now, and then take a look through our case studies. So what are PFAS? PFAS by the EPA are per and polyfluorinated substances. They are, a couple of them are shown on the right-hand side of the screen here. They're chains of carbon molecules that are linked together that are fully fluorinated or have fluorine compounds at all of the locations that a carbon atom can be bonded to, except for one or more of the carbons at the end of the chain, and they have a functional group on them. And these compounds are synthetic. They're pretty much only man-made. There may be one or two that occur naturally, but basically think of these as completely man-made products that are really good at their job. They are oil resistant, water resistant, chemical resistant, heat resistant. They are great at what they do. And because of that, some of you may have heard these PFAS called forever chemicals, that they don't break down. So there are two types, as I said, there's perfluorinated and polyfluorinated. Perfluorinated are the ones with just one carbon at the end that doesn't have a fluorine on every single bonding site. And these really were used as surfactants, as surface coatings. And you can see on the right here that you've got one end that likes to be in water and one end that likes to be in air or in oil. They're charged differently on each ends of the molecule. So they have a tendency to align themselves on the surface of things. And that's what makes these great surface coatings that are water resistant and those kinds of things. Now, the polyfluorinated compounds, they have more than that one carbon that's been impacted in this long chain. They have here in this picture, we've got on the left-hand side, sulfur and nitrogen and some other carbon compounds that are at the head end of this. And that allows both from a abiotic and a biologic breakdown to occur. And what happens is these polyfluorinated compounds get broken down until you have a perfluorinated compound, which is an end product. It's terminal. It's permanently going to be that perfluorinated compound. So we kind of show that there's these arrows going, that there's a way to break this NET fossa down to one of the popular or most used perfluorinated compounds, PFAS. So as you can see with just a couple of examples I gave, there are thousands of possible combinations of PFAS. And this shows some of the different classes of PFAS. There's non-polymer and polymer PFAS. The non-polymer PFAS are the ones that you really hear most about in the news and that you hear about being associated with things like the firefighting foams that may have been used on Air Force bases or with chemical fires. And that's where the per and polyfluorinated compounds live. And we're not going to get too much more into the chemistry here, but you can see on the left-hand side, that's where per and polyfluorinated substances are. There are various families of those. And you can envision those as these really complex, straight chained carbons, branched carbon molecules, the perfluorinated with only one small head on it, the polyfluorinated with lots of different things going on. And then we've got the polymers, polymeric PFAS, on the right-hand side. And those are more things like Teflon, huge molecules, 800-900 carbons in their chains that are very stable and are kind of like the perfluorinated substances in that they don't react and they don't change in their makeup, again, for the most part. And I'll get to why I kind of hedge how I'm saying this with all these compounds a little later, but those are really the two big families of PFAS. We're going to talk about the ones on the left-hand side here. The naming conventions, I won't go into these much, but for those of you who remember your Latin or are kind of chemistry oriented, there's lots of great names in here. Perfluorobutane sulfonic acid. The acronym is what's really important. PFBA, PEA, HXA. There are 4, 5, 6, 7. That really is talking about the number of carbons that are in these compounds. Again, this whole list represents basically 4 carbon through 10 carbon straight chain PFAS. And we've got all these different options for what their chemical makeup is. So you can imagine there's just thousands of combinations of these. So I said these were really great at their job and that they had lots of jobs, and here's where they've been used. This is why we start to see why they're in our environment and why we're concerned about them. You've got firefighting foams. You have stain-resistant carpets. In the bottom left, that's the Denver airport, those teepee-looking, tent-looking structures there are coated fiberglass cloth, and that was made using PFAS. Waterproofing on your boots, oil proofing in pizza boxes. Again, here's some more photos of different items that PFAS have been used in. There's really kind of two major uses of PFAS that have impacted the environment that we're looking at right now. One is firefighting and odor control foams. Those are the AFFFs that you may have heard of, aqueous film forming foams. And then you have more commercial industrial products where it isn't really the PFAS that's the primary part of the product, like the foams, but they're used to enhance the products. Metal plating, waterproofing on fabrics, on paper, cleaning products, pesticides, waxes, just about anywhere where there's a coating and it's water, oil proof, these things probably have been used. Where is it? Well, airports, naval facilities, firefighting academies, those AFFFs, very obvious. Manufacturing facilities, but also at wastewater treatment plants and in landfill leachate. When the carpets and the clothing and things get thrown away, they go to the landfill and these compounds can come out in them. So what are the release sources? Again, firefighting, spills, landfills, wastewater treatment facilities. And then you have kind of these non-traditional redistribution methods where on-site disposal fields for septic fields and irrigation wells and land application can happen. So these are all pretty complex kinds of things to think about. So we've come up with a graphic to try and let you think about where and how these things get moved through the environment. So if you look here in the upper left, we've got industry who uses these PFASs in manufacturing things. And you may see PFAS come out of the stacks. They may have off-spec product that could go to the landfill. And then you have discharges. Maybe they have wastewater that goes to the wastewater treatment plant or out to a river. You know, if industry makes a product, it goes across to your home, you use it, you get exposed to it. Some of that material will wash off in the laundry. What you end up having in your body will come out of your body. It can go to the wastewater treatment plant. These perfluorinated compounds, they don't get broken down in a wastewater treatment plant. They actually will pass through it, and they may discharge into the surface water. Some of them may get absorbed to the sludges that are in a wastewater treatment plant and go to the landfill. The landfill has leachate, it goes to the wastewater treatment plant oftentimes. You start to see this whole cycle of how PFAS can move through the environment in your community. And you know, one other thing from wastewater treatment plants, they have biosolids, which is basically the sludge gets processed and dewatered and the pathogens get taken out, and you have a great organic product that you're left over with that has been used for years and years as fertilizer and can be used as fertilizer on farmers' fields, or even sold as a commercial product as a compost. And then that gets used on plants and things, and the plants can uptake it and again cycle back into your home. So this graphic is something I want you to kind of keep in the back of your mind as we talk about how pervasive these PFAS are and how they may impact your environment. So what I'll do next, that's kind of a chemistry lesson. We'll move on to toxicology and kind of how are these things being regulated. So from a toxicological standpoint, I'm not going to get deep into the science, but with thousands and thousands of compounds, we don't know what the toxicology of every one of them is. We do know pretty well what the toxicology is of the most frequently used, of the ones that are most often found in our environment. And those PFAS really get down to those straight chained perfluorinated compounds that I showed previously that are from the 4 to 10 carbon chain lengths. There are some others, Gen X you might have heard of, being used as a replacement to some of the historic PFAS. That one's a little more complicated in its makeup, but it breaks down to these perfluorinated permanent kind of compounds. So we have some limited toxicology. We've seen links with diabetes, weight gain, some cancers, PFOA, which is an 8-chain carbon additive that was used a lot in manufacturing. That's been indicated as likely a carcinogen. PFAS, which is the 8-carbon sulfonate compound, that's the one that really got used a lot in AFFF use. That also is starting to become associated with some cancers. And there's lots of other potential impacts, from developmental, reproductive impacts to systemic impacts. And the thing to remember about all these, again, these compounds are very, very stable, so they will have a tendency to bioaccumulate in lots of different animals and even in plants. But in us, it accumulates in our bloodstream and it will stay there, some of these compounds, for months to years before it's excreted. And that bioaccumulation is the issue. When you get exposed, it's not like being where someone's spray painting a piece of furniture. And if you leave the room, you're no longer exposed, and in a few breaths or maybe 10 minutes, those compounds have been released from your body. These stay there for a much longer time. And that's what increases your exposure over time, even though you're seeing very small amounts. So the EPA does have a lifetime health advisory for 2 of these thousands of compounds, the PFOA and PFAS. And they've come up with an advisory of, in drinking water, of 70 nanograms per liter. Now, nanograms is a pretty interesting point of measurement, but this is the way to think of it is nanograms per liter is parts per trillion. So if you have 1 gallon of PFAS, you would have 1 trillion gallons of water that you would add to it to get 1 part per trillion. So it's a very, very, very small number. It's a very small amount. So the EPA looked at it, and I won't go through the gory details of how they figured this out, but basically they come up with an amount per kilogram or pound of body weight per day that you could take in over your lifetime and not have an increased risk of one of these health effects. And where they landed was that you could drink water for 70 years at 70 nanograms per liter and not increase your risk of some disease due to PFAS or PFOA. And that assumes that only 20% of the PFAS and PFOA that gets in your body comes from drinking water. So all those different levels of math end up at this very, very low concentration. Again, health impacts, it bioaccumulates. These compounds are ubiquitous. They found PFAS in the blood of polar bears, in penguins. They find it in the ice in Antarctica and in the Arctic due to its pervasive use and discharge and its permanence when it gets into seawater or it gets into the air, they don't break down. They end up going wherever those things go and depositing in those new places. So drinking water has really been the focus of how folks have been impacted and the highest risk of what you're intaking. So PFAS and PFOA, because of these hazards, were dropped out of production in the United States. They haven't been used in production since 2002, which is great. Unfortunately, the replacement compounds for these things are some of those other thousands and thousands of PFAS. So those have been getting discharged, and we have been getting exposed to them over time. What we're seeing is PFAS and PFOA concentrations in people's bloodstreams, in places that we've seen impacts, are going down because, well, there isn't more being put in the air or in the products we use. But those substitute PFAS, the smaller chain PFAS, the more complex chain PFAS, we're seeing those concentrations increase. So that's the bad news. We've got these great compounds that are bad for us, that they stopped using the ones that seem to be the most frequently used, but these replacement compounds seem to be being used in as equal mass, and we don't really know what their toxicity is. So where do we see these things? What's happening? You know, what are the regulatory environment right now? Here I focused in a map that's actually on you can get to on the Northeastern University website. They have a great PFAS website. And what you can see here is all of the public drinking water wells that have been sampled in Rhode Island and Massachusetts that have PFAS in them. Now, this doesn't mean that it exceeds the health advisory or even the local state maximum concentrations, but this is where these compounds are present. And as you can see, it's kind of everywhere. You don't have a lot of industry out here on the arm of the Cape that might be discharging these compounds. If we saw clusters in the Boston area or maybe around Warwick and Providence, we could say, gee, these industrial areas, they're the ones being impacted. No, where you look, we're finding these compounds. And they're in our public drinking water supplies. So public drinking water, those things, we're looking to the EPA as the folks who are going to be our guiding light as to what's a safe level, what is it? Well, the EPA has a very arduous methodology to come up with what a safe level is in drinking water and getting that regulation out into the world. And unfortunately, right now, there isn't a federal limit. They have an advisory, but there's no regulatory hooks behind that. They have put out advance notice of proposed rulemaking, not for a drinking water standard yet, but they are considering making PFOA, PFAS, those two big users, Gen X, which was one of the first and most frequently used replacement compound, and PFBS, that's a butyl sulfonate, a 4-carbon sulfonate, making those hazardous substances, which will give the EPA more meat behind them to actually enforce the release and use of these compounds. They also are looking at having all public water supplies over a certain size sample in the next 2 years for 29 additional PFAS. So they're starting to develop some things, but they don't have that nice regulation that we can bring to bear or that would be brought to bear on public water systems. So what's happened is the states have picked up the torch and they're regulating PFAS on their own. And as you can see on this table, there's a lot of different ways to do that. Vermont, for instance, uses a sum of 5 PFAS at 20 parts per trillion. Connecticut uses a sum of 5 at 70 parts per trillion. Rhode Island uses the EPA health advisory. That's 2 compounds, PFOA and PFAS, at 70 parts per trillion. So as you see here, it's all over the board as to what is safe, what is not, what concentrations are you going to be regulated to, where's that going in the future. That's a real concern for you folks who are out there with drinking water wells, who have clients and users that you're supplying drinking water, or for you folks who run wastewater plants. Are these concentrations what we need to have going out of our plant? Who's going to regulate that? It's really state by state right now, which makes things very difficult. The EPA has put out a strategic roadmap of how they're going to regulate these compounds. Right now in drinking water, as I said, it's the states who are driving the bus. The EPA says they're going to do 31 key actions between now and 2024. That's very, very ambitious. The EPA has been trying to come up with a safe drinking water level for a little over 10 years now for PFOA and PFAS. I'm not sure they're going to get there. So at the end of the day, we've got an evolving landscape. Toxicology is really something that's tough to handle. Determining what the concentrations are that are safe from an analytical testing and from a who's regulating what standpoint is very difficult. And, you know, confusion abounds from state to state. So for you folks, what are the big issues? What are the things that really are going to drive regulation and drive where you have to spend money to deal with PFAS? Well, it's public water supplies, and whether you have PFAS in them, is those concentrations going up, down, staying the same? And when those regulatory obligations come into play from your states. What will happen with wastewater treatment facilities? This is the next thing that I think is coming along. Once all of the states have an idea of who's drinking what in their water, they're going to look at wastewater treatment facilities and what are they discharging into our surface waters? What are they doing with their biosolids? What's happening with landfills? All of the states here at SNEP, they're analyzing landfill leachates. They're analyzing hazardous waste sites. They're looking at what are the levels of exposure, what do we need to require these folks to do to address it. So really this, I think, is the priorities that the states are taking right now. And they should be the priorities that you're looking at for how to get your handle around whether we have a PFAS issue in our community. So dealing with it, treating it, how do we get this out of our water? I'm just going to do 2 quick slides on this. You can't destroy these compounds very easily. They have to be absorbed onto another media, and then that media either landfilled or disposed of somehow. Granular activated carbon, these compounds do get stuck onto that pretty well. Same with the ion exchange resin, which is like a water softener, only the resin's been developed specifically with PFAS in mind to grab a hold of it. And reverse osmosis, there's some membrane filtration that can be done. There's other innovative methods that are out there. They're very much in the infancy and not really being used out there very frequently. So what does one of these systems really look like? You've got some booster pumps that filter out sediment, soften the water and do some of the removal in resins, and then oftentimes granular activated carbon is used to polish and make sure that you're at those 20 or 10 or 5 part per trillion concentration when you bring your water out to the distribution system. So that's water treatment. Wastewater, and I bring this up because I do believe that for you folks, this is going to be the next real concern out there, and is something that's going to be a very difficult problem to get our hands around and to resolve. But wastewater plants don't really do a good job at removing PFAS. They actually may increase the amount of perfluorinated compounds that you see being discharged. They take those polyfluorinated compounds, the ones that can be degraded, and because a wastewater treatment plant's all about biologic growth and degrading nutrients and those things, using them as a food supply, you actually see what happens in this graph here, which is the influent concentration of perfluorinated compounds is below 20. But when all those other compounds, those precursors or polyfluorinated compounds go through the treatment system, you suddenly see a much higher concentration in what's going into the surface water. And if you happen to be a community that uses surface water for drinking water, what happens if you're downstream of this particular facility? Do you start seeing PFAS at levels that would be of concern? Again, if you have sludges and those things from the wastewater treatment facility, where are they going? And how are they impacting your community? So let's get to some more fun stuff. Let's look at some case studies of how is this applicable? What have folks had to do? And you folks in Rhode Island are probably very familiar with this site, but it's Burrillville, and it's a small community in the northwest section of the state, in Pasco County, and they had their water system sampled by DPH and Brown University a number of years ago, when they went around to 38 water systems, small water systems that hadn't been sampled due to EPA regulations, but they went out and sampled them because they looked like they were near facilities that might have released PFAS. And in Burrillville, the Oakland Association is the name of the water system. They had a public well, a bedrock well, that had greater than 100 parts per trillion PFOA and PFOS. Again, this is in Rhode Island. They're just regulating to the 70 nanograms per liter. So in the immediate response, when they found and confirmed that concentration, is that they went out and told the users of that water system, which there are about 34 or 35 homes that were served, to stop drinking their water, and they started making spring water deliveries for their drinking water. All of the private water supplies within about a quarter mile were sampled, and then they had lots of great public meetings and public forums to keep the folks in town aware of what was going on. And then they started looking at the feasibility of extending a nearby public water system into the neighborhood that was being served. So that all four of those things started happening within a week of finding out that this elevated concentration was present. We were brought in to try and identify the source of contamination and to help with some of the drinking water sampling of the private wells, and to try and, as I said, figure out what the source was and what the extent of the contamination was. So this is a little bit of a busy map here, but here in this purple is the well for the Oakland water supply. And this main road that you see near the well is folks who were served by it. And in the yellow squares, you can see potential sources of this PFAS that was being found. There's a landfill over to the left. To the right, there's a former mill that made textiles and that had a very large fire. So they may well have used PFAS, and PFAS may have been put on the fire in the form of AFFF foam. There's also a small fire department right in the middle of the picture here. However, that's a new facility. And although they stored AFFF foam there, they've never used it there. They've never performed any mock responses or tested their equipment at this new facility. They've done that in a totally different part of town that they haven't put foam on the ground here. So they didn't feel that they could be a source. And there are some other industries around the area. So we really needed to, put on our thinking caps, who could be the source here. So this map shows all of the private water supplies in the area. The public well is the well farthest to the right in red. And then you can see the fire department well is in red. And like all good graphic folks, red is bad, yellow isn't as bad, and green is good. So we have this amount of contamination that seems to kind of be centered around the fire department and maybe going to the north, to the upper side of the page. So we went and put in a number of monitoring wells and did quite a bit of work. And we looked at not the bedrock water, which is where all these wells are getting their water, but we looked at the shallow groundwater, the kind of groundwater that gets in your basement when it's springtime. And here, again, from a red, yellow, green, we see that the contamination in the shallow part of the aquifer is actually going in the opposite direction. It's going down towards the river and is centered very near the fire department. And with our research and all of the information that we gathered, we determined that the fire department actually has a drain that goes to a leach field on the property, and that the residual firefighting foam that was in their hoses and in their nozzles would be rinsed out of those things when they came back to the fire department after an event, and that would go down this surface water drain and into this leach field. The leach field, when we drilled beneath it, didn't have any shallow groundwater under it. There was bedrock. There was this peak of bedrock that happened to be only a few feet under this leach field. And so the PFAS was able to get drawn directly into the bedrock and impact those bedrock wells. So the solution here, after all this investigation was done, is that very near this area, within a quarter of a mile, was the end of a public water supply. And that public water supply had sufficient extra capacity to come in, be extended, and all of the homes that you see on this map, even the ones that had the clean drinking water wells, they were added to that water supply and are now being supplied water from a clean source that's remote to where this happened. I like this case study from the standpoint of this is a very, very small community. It's a very small community well, and it was a very, very small source. There was a lot of talk about these industrial plants and huge fabric manufacturer who could have been the source of this bedrock contamination. And it could have been acres and acres and acres of impacts. But come to find out, we had one small drinking water well that was right near a very small release, and it unfortunately has impacted this well to a point where it needed to be abandoned. So our next case study is about wastewater. This community wanted to take a look at who in our community might be discharging PFAS and thereby bringing it to our wastewater treatment plant. And then we have biosolids and things that are impacted. Let's see if we can get those folks to not use that PFAS so that we can have a good, safe biosolids product. So here is a picture of one of the industries that we sampled outside of. Every industry in town actually helped coordinate with us and allowed us to take samples. And so what we did is we sampled at a number of different locations throughout the community. And this actually happened in Vermont, which should be obvious from the field tech wearing a tie-dye shirt. Here are some of the results. And again, the very specifics of each one of these PFAS is not really the story here, it's the concentration. And so we see the influent concentration, so that's of the water entering the wastewater treatment plant. Then the effluent, as we saw before, a little bit higher due to that polyfluorinated compound breakdown. And then we see we went out into what I call the sewer sheds. Think of them as watersheds, but these are collecting sewage. So we went to the Cascade Street pump station, and that happens to only collect water from a residential neighborhood. Pearl Street is commercial row, restaurants, the high school, car washes and doctor's offices, convenience stores and grocery stores. Susie Wilson Road is another commercial one, but has a couple of more industrial uses. And then we had 3 industries that we sampled. 2 were personal care products, soaps, which PFAS are used in soaps because it's a good surfactant. It helps get the dirt taken away. And 1, a valve company that makes Teflon valves. So we look strictly at the concentrations and we go, my goodness, these industries, they've got to be the culprit here. They have high concentrations. They must be what's feeding the concentrations that we see in our wastewater plant. But the concentrations are only one part of the story. The other part of the story is how much flow is coming in with those concentrations. So when we look at just the perfluorinated compounds at each of these, and envision this as a map of the town. And up here where there's Rogers Road, this is actually for a different town that we did the same thing in, so the names are a little different, but Rogers Road is a residential area. And you see the size of the circle is the concentration of the compounds. And Pump Station 3 is a residential and hospital. The north sector is industrial, and Pump Station 9 is commercial. So what we see here is that when we think about concentration and flow, the mass, and that's what these circles represent, is the mass input, the number of pounds per day of input of PFAS. These 2 upper ones that are in residences put in much more of the mass than the industrial commercial areas, because they may be a little higher concentration in the north sector, but they don't discharge very much water. So your wastewater treatment facility all the way down here sees a mixture of all of that. So it was very counterintuitive that the industries didn't really give us the perfluorinated compounds we thought we might see. So we looked at the polyfluorinated compounds, and we saw something very different there too. The residential side of things put a lot more mass of these polyfluorinated replacement compounds into the system than the industries did. Now, the industries put in more than they did the perfluorinated, but it still didn't match up. And this Pump Station 9 is commercial row. That's the car washes and the restaurants and all. They have a pretty large mass too. So again, what this does is it kind of tells us, as we look at how do we get fewer PFAS to come out of our wastewater treatment plant, we want to limit what's being discharged. It may not be the industries that are feeding that. It may actually be you and me, and washing our clothes, and what's in our bloodstream, and the soaps and waxes and things at the car wash. There's a lot of study that needs to go on. Again, this is one little study that we did in one case study, but it's indicating that, you know, it may be more than just going and looking at ABC carpet manufacturer and asking them to no longer use PFAS or to change how they're discharging their waters. That's going to be needed to reduce what we see in our wastewater treatment facilities and subsequently in our surface waters. So I've given you just a tremendous amount to think about. You know, the training courses on these PFAS go for 1 to 2 days at a time. I tried to feed you a little bit of everything in just an hour. But here from Massachusetts, I was able to pull up a bunch of resources, and I apologize for my Rhode Island friends, I wasn't able to get a slide together for you, but do go to the DEP websites to see what is out there for resources. For Massachusetts, there's something called the Interim PFAS 6 Response Program. They've done 2 sets of funding from that. Unfortunately, the last one, the applications were due in February, but they've provided millions of dollars for folks to respond to PFAS in their public water supply. The Clean Water Trust provides loans. The revolving loan fund, the SRF, which a lot of the municipalities will be familiar with, they have, they've got $176 million in monies they've given out for PFAS response. The COVID recovery monies, both state and federal, have a tremendous amount that is coming along that we'll see soon that that will be available for looking at these things. To get any up-to-date information, go to mass.gov, type in PFAS. They'll let you know what's going on. Also in Massachusetts, if you're concerned as an individual and would like to see your private well sampled, they are doing that for a number of residents. You can get on the website and ask for your well to be sampled. And if you're in an area that they feel they want to get data from, they will come and do that for free for you and provide you with the results. We didn't get into the complexities of sampling and analysis, but trust me, I could give you an 8-hour class on how difficult it is to sample water or soil or your shirt and try and come up with a concentration in the part per trillion level that's accurate. It's an extraordinarily difficult thing to do. So having folks who know what they're doing take a look at that is really the way to go. So do get on to the Mass DEP, get on to the Rhode Island Department of Health and Department of Environmental Management websites. They can talk to you a lot about where these things have been found, what's being done, and how you can maybe get some assistance with regard to addressing these things. Important websites, again, these are all in the PDFs, but the ITRC is a fantastic resource, tremendous resource to find out everything you want to know about PFAS. And the Northeastern University PFAS project, also great, some great mapping tools, really, really good resource to find out more about PFAS, and oftentimes PFAS right in your area. And finally, I just wanted to end with this graphic again to just reiterate that these compounds are pervasive. Studies in Vermont and Michigan have shown that these compounds are literally everywhere. You can go into undeveloped, unused portions of the Green Mountain National Forest, sample the soils, and find PFAS in those soils, in essentially a virgin, unused, nearly untouched by man area. This is the reason why they are so pervasive. They're permanent. They don't break down, and we just recycle them through our environment by various methods. And so keep that in mind. Keep that in mind when you're thinking about your watersheds, when you're thinking about development and where would be a good place to put a new park. How are we going to get water to our new low-income housing area or our irrigation for a farm? PFAS, unfortunately, are becoming something that need to be thought about and thought about seriously in all those particular instances. So with that, not necessarily bright news, but with that information, I am more than happy to take any questions you folks might have or try and explain something that maybe I didn't do so good a job with. Tess, I can't hear you.
Sorry. So
There we go.
sorry about that. Guys, all I've said so far was to just check the handout section for the PDF, because we saw a few of you asked for it in the questions box. So go ahead and click handouts if you're interested in taking a look. Okay, sorry, Steve, now on to questions. Thank you so much for that incredible overview. It's incredible to hear how complex this is. So our first question is, can biochar sequester PFAS?
Biochar is being looked at in great detail, and it is a really high carbon containing material. So I can envision that that will be as efficient or more efficient than granular activated carbon to sequester and grab that PFAS, and then you can take that biochar and dispose of that.
Awesome. And then this commenter also notes that it is a cheaper option than activated carbon, so that's why they're asking.
It may well be.
Awesome. Okay, and then we did get some questions from some other New Englanders, particularly about any information for Maine and New Hampshire. And I thought I saw just a flash on your one slide that you had showed some of the action levels for those states. So recommend downloading the slides and paging back to that PDF where Steve has laid out some of those regulations.
Absolutely. New Hampshire has some pretty low levels that they regulate to, and they've done a tremendous amount of sampling of all the media I talked about today. They have a great website for their Department of Environmental Services. And if you type in PFAS there, you can look at all the data they've collected through the whole state.
Awesome. And then I just wanted to ask, we have a lot of different folks on the webinar today. We have people from, watershed councils to drinking water systems to local government officials. And we know that these contaminants are in essentially every community. Do you have any advice, especially for local municipal governments that haven't had to address this issue yet, what they can expect or what they might expect to have to do?
Yeah, I would expect, obviously, as I've said, the drinking water quality for anyone who's got public drinking water supplies, and if you've got a high density of private drinking water supplies near where there's the fire department, if you've got on-site wastewater disposal, that maybe you have a community wastewater disposal that's soil-based, take a look at the water quality. And if it hasn't been sampled for PFAS, they're gonna get to you. Every public water supply in all the New England states are gonna be sampled probably by the end of this year, if they haven't already been once or twice. And then the next thing that's gonna be coming is, I believe, is wastewater biosolids sampling and determining how that's going to be managed in the future. And the third one is, if you've got the old town dump, it's very likely that you have leachates that are coming out of that have PFAS, and you'll want to look to see if you've got drinking water supplies near there.
And I think some of us probably do. And I know, in New England, we have a lot of water, we have lakes, we have rivers. So anyone near with a septic or on site near that, you would be maybe extra motivated to get that checked out. Okay, and then we know that there's been a lot of talk from the federal level about, given the impending streams of funding available through, as you mentioned, Steve, the coronavirus relief, through the American Rescue Act, through the bipartisan infrastructure bill. We know that this could be a priority for the federal government. How do you imagine or envision communities will get their hands on some of this funding?
That funding, as far as I have seen, is really being funneled through either the state agencies like the Department of Environmental Services, anyone who's dealing with the water system folks, so the it's going to be through revolving loan fund methods, because that's already set up. It's a way that a lot of these municipalities are used to getting their monies. And then if you have regional planning commissions or community planning, county planning commissions, those kinds of agencies will also get some funding, primarily for more of the site assessment, site cleanup side of things. Infrastructure wise, I would look to revolving loan fund style methodologies is what I'm hearing most every state is using as their mechanism to get these things out.
Fantastic. And it is right at 2:01. So with that, I think I want to thank you all for joining us. There will be a survey that pops up for you all after you take close out of the webinar. So please let us know what else you'd like to learn there, and any extra questions you have for Steve, you can always pop those in. Steve, any closing comments?
I'm all set. I wish I was bringing better news when I give these things, but keep your eyes peeled. And as you said, there's millions of dollars coming along to try and help out with this in the very near future.
Awesome. Have a great afternoon, everyone. Thank you so much.
Great. Thank you, everyone.